You are literally losing marks right now. Zero fluff, let's just get straight into it. We're stress testing your physics exam knowledge today because there is this massive trap in the Cambridge 0625 syllabus that almost everyone falls into. Let's analyze a really common flawed answer. The object's weight on the moon is 12 kilograms. It sounds perfectly normal, right? I mean, you've probably written something exactly like this yourself. But writing this super common mistake will instantly cost you crucial method marks and completely tank your grade boundaries. By the end of this explainer, you're going to know exactly how to write the correct approach to secure full marks.
Section 1. The ultimate exam mistake and why ordinary revision just fails.
So why does ordinary revision fail us here? Well, because it lets you blend everyday language with strict scientific definitions. Like in everyday life, we use mass and weight totally interchangeably. But let me tell you, the Cambridge Examiner absolutely does not. Mass is strictly the amount of matter in an object. It's measured in kilograms, it's a scalar quantity, meaning it only has magnitude, and it stays the exact same everywhere in the universe. Weight, however, is a completely different beast. It's the actual force of gravity acting on that mass. Because it's a force, its unit is the Newton. It's a vector quantity with a specific direction, always downwards towards the center of a mass, and its value actually changes depending on the local gravity.
This fact right here brilliantly illustrates just how variable weight actually is. Did you know the Earth isn't actually a perfect sphere? It kind of bulges at the equator and is slightly flatter at the poles. Because you're physically closer to the center of the Earth's mass when you stand at the North Pole, the gravitational pull is slightly stronger there. So your mass is identical, but your weight is actually greater at the poles than it is at the equator. It's crazy, but it proves that weight is highly dependent on your exact location in a gravitational field.
Section 2. The Newton and gravity, an action at a distance.
Now, to really understand weight, we have to understand the force that causes it. Gravity is what we call an action at a distance force. It doesn't require physical contact to pull you down, right? Not like when you physically push or pull a block across a desk. It acts completely invisibly through space. It sits in the exact same category as the magnetic forces between two magnets, or the electric forces between electric charges. And since weight is a force caused by this gravity, it has to be measured in the unit of force. Let's give you a memorable mental anchor for this: 1 Newton. Imagine you're holding an average-sized apple in your hand. That downward pull of gravity you feel from that apple, that is exactly 1 Newton.
So how does this scale up? Well, on most of the Earth's surface, an object with a mass of 1 kilogram experiences a gravitational force, a weight, of 9.8 newtons. Now, in many 0625 exam contexts, you're actually allowed to round this up to 10 newtons to keep things simple, but always check the specific gravity value given on your paper. Following this logic, a 2 kilogram mass has a weight of about 20 newtons, and so on. But how do we actually prove this mathematically for the examiner?
Section 3. Calculating weight accurately using the W equals mg framework.
We need a solid framework to guarantee those method marks. So let's walk through this step-by-step derivation so you actually understand the underlying physics, rather than just memorizing a bunch of letters. Step 1. We start with Newton's second law. Force equals mass times acceleration, or F equals ma. Step 2. Since weight is just a specific type of force, we substitute force, F, with weight, W. Step 3. The acceleration in this specific scenario is the acceleration of freefall caused by gravity, so we swap out A for G. And step 4. This elegantly brings us right to the examiner's required formula. W equals mg. Weight equals mass times gravity.
In a moment, I'll show you the examiner clue that changes the answer completely, but first, you need the framework that makes that clue obvious. Like, what exactly is a gravitational field? If you skip over this, you'll miss the exact Cambridge wording required for those top-band answers. We know gravity acts through space, but how do we define that space in a way that actually satisfies the mark scheme?
Section 4. Defining gravitational fields, which is basically the examiner's secret.
Okay, get ready because here is your mandatory flashcard definition. We say that when a mass experiences a gravitational force, it is in a gravitational field. But the strict definition of gravitational field strength is the force acting per unit mass. Notice the equation, G equals W divided by M. This is literally just a quick rearrangement of our W equals mg formula. And remember, because force is a vector, gravitational field strength is also a vector quantity. It has both a magnitude and a very clear downward direction.
Section 5. The examiner evaluation checkpoint. Let's jump into the Moon versus Earth challenge.
Let's escalate the stakes a bit.
Welcome to the 0625 pressure test. Imagine you have an object with a mass of 12 kilograms. Earth's gravity is given as 9.8 meters per second squared. The Moon's gravity is exactly 1/6 of Earth's. Your task is to calculate the weight on Earth and the weight on the Moon. I seriously challenge you to pause this explainer right now and predict the answer using the concept, data, and reasoning framework we just built. Think carefully, and whatever you do, don't let the examiner trick you into changing the mass.
All right, let's break down the results. That painful student mistake we discussed at the very beginning, saying weight is 12 kilograms on Earth, 2 kilograms on Moon, gets absolutely 0 marks. Why? Well, because it uses the unit for mass instead of force, and it incorrectly assumes mass changes based on location. So the crucial takeaway is the correct answer. Earth weight is 117.6 newtons. We got that by multiplying the mass, 12, by Earth's gravity, 9.8. For the Moon, the mass stays exactly 12 kilograms. It doesn't change. But the Moon's gravity is 9.8 divided by 6. So 12 times that new, weaker gravity gives us a Moon weight of 19.6 newtons. Completely flawless.
This brilliantly illustrates what the examiners are actually looking for when they grade your paper. Top band candidates successfully separate constant mass from variable weight using W equals mg and correct vector units. The examiner isn't just testing your math skills here, they're testing your conceptual understanding that mass is constant matter and weight is a location-dependent force measured in newtons.
Section 6, the unresolved problem, and our binge loop pathway.
So we've successfully conquered the mass versus weight trap, but here is the unresolved problem. Applying this conceptual rigor to an entire structured exam paper requires a complete strategy. The exact correct answer pathway is waiting for you in the next explainer. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Your mandatory next step is to clip the video on screen right now for our ultimate last 7 days revision map. After all, if a simple mix-up between kilograms and newtons can cost you a whole grade boundary, what other invisible traps are hiding in your next paper? Go click it now, and I'll see you over there.